This is the answer key for differentiability. Compare the right-hand, left-hand derivatives, so the function is not differentiable at the point P. So the P is 1, 2. That's here. This is point P. And over here it's 1, 1. So again, left and right-hand derivatives never exist, except they're saying that they have to both come in. If they don't, so you got that. So the slope on the left-hand derivative, also known as when x is less than or equal to 1, slope is 0. Slope of the right-hand derivative when x is greater than 1, slope is 2, if I'm not mistaken. So f is not differentiable at point P or x equals 1. We usually define by the x variable. All right, so this looks ugly. It shouldn't be that bad. The slope of the left-hand derivative when x is less than or equal to 1, slope is 1. Now on the other side, I need to take the derivative, which we really haven't learned how to do yet, but I just haven't made it official yet. So the slope for the right-hand derivative when x is greater than 1, we have to go the derivative of x to the negative first, which is -1, x to the negative second, which is -1 over x squared. We're at 1, so m equals -1. 1, -1. Therefore, f is not differentiable at x equals 1. Cuspy corner, definitely corner. There it is. Graph function, closed intervals given. What point does function appear to be differentiable? Continuous but not differentiable. Neither. All right, so this is continuous. And by the way, the endpoints get a little dicey. What's going on at 3.1? Or oh geez, I can't believe I missed it. It should be 3. It's not. What's going on at -2? Who cares? We don't worry about the endpoints. Now this one, we do that horrible thing where we say, oh, it's continuous everywhere except, so yeah. And again, I missed my 3 on this side. I got the -2 nice, but 3 wrong. I'm not sure what happened there. So continuous everywhere except x equals 0 because of the jump discontinuity. 2.7-ish. Right about there. And it's differentiable over the entire domain Yes, I said everywhere, which I should say over entire domain. Doesn't really matter. Except at corner point discontinuity. -1, jump discontinuity. 0 and 2.7. All right, so functions below fail to be differentiable at x equals. Tell me the problems. Corner cusp, vertical tangent, or discontinuity. So, boy, I sure hope you know how to graph, because otherwise your life is in for a really, really horrible time. I know that arctangent is just the reflection. This would be tangent. This would be tangent. So you reflect it, and rather than the pi over 2 being there, it's up here with an asymptote, down here with another asymptote. And then it's 1 when x equals 0. So that would be right about there. So we would say this is a jump discontinuity. At x equals 0. Corner cusp vertical discontinuity. You could also call it a point discontinuity. Either one. It's not that big a deal. Graph y equals x to 4/5. I actually don't have this one memorized. You should be able to throw this in a calculator, although it's really not that hard to put it together. And then you would say cusp at x equals 0. Call it a corner. I'm not going to lose any sleep over it, but it's just the way we're going to do it. So here, definitely graphing this one. This, by the way, is equivalent to absolute value. Think about it. Yeah, I mean, you're squaring it and taking square root. It's like those cancel, huh? Negative becomes positive. So you're going to get something like this. So we'll say it's a corner at x equals 0. And then here, these vertical tangents are a little tricky to draw. So we go with vertical tangent at x equals 0. Find the numerical derivative of the given function to indicate a point. Use h. I'm going to be lazy and use my calculator. There's no reason, right? So by the way, if you have a TI-83, it takes a little practice to put it in. You go function, variable, number. You could go function, variable, variable. I'm using calculator because, as we've discussed, that's what the calculator does. So we will get, according to the calculator, f prime at 3 equals -2. And yes, differentiable. Actually, I'm going to double check with my calculator so I'm not lying. With respect to x, 4x minus x squared. With respect to x at 3 I got -2. So hey, how come we got a decimal when we did it in class? Well, sometimes you do, sometimes you don't. All right, off we go again. And oh, by the way, the reason I said yes, it's differentiable is not because I got a number, but because I know there's no problems with the graph, cusp corners, vertical tangents, or discontinuities. Same thing here. So yes, it's differentiable. Now I got a little bit of nervous thing going on here. If I graph it, get this. By the way, if you're trying to figure out how come that works, it's because there's an even on top and it's going to square away any negatives. So, I mean, you could say, well, do the cube root. -1 cube root is -1. Then you're going to square it. So you're always going to get an absolute value-esque thing. So if you do calculator, you get f prime of 0 equals 0. And no, not differentiable. And over here, there's no problems with this because it's the exact same problem as this, except it's at 2. So I'm not sure why we tried to torture you with that, but I think it's a good thing to practice with the calculator. And then we got an absolute value. So yeah, we got a problem here. Is it at 3? 3 minus 3 is 0. Yeah, it's when it does that jump thing if you look carefully. -3 should go left, but anything inside parentheses goes right. So we got a corner. But my calculator says, no, it's fine. Pretty sure it's going to say 0 because it's thinking horizontal line here, but not differentiable. So again, they want you to graph the derivative. And they're basically saying, hey, do you think you're smart enough to see where we're going with in the next few units? All right. So if I go with y prime equals, and this is something I'm only going to write once, numerical derivative. You put the function in, say with respect to x, and then x is not at a specific point here. We graph it, and we're like, oh, wow, check it out. It looks exactly like sine of x. And this goes back a little bit to, I say, when in doubt, graph things, and you can see if you can sort things out. This is weird. I don't know what the heck's going on here. So now I'm just going to graph it. There's really no reason to do anything else. You graph it and you get this. Oh, there's probably some of you don't know what I mean by graph it. See if we get better daylight today. Nope, terrible daylight. I need a better calculator. So let's go up here and do one clear and clear. And we go math 8 derivative with respect to x, and let's do this one. Fraction x math absolute value of x over 2. Who figured this out? I don't know. It's some mad genius. And then with respect to x, because we're just graphing it. And graph. Check it out, absolute value. Could be some holes on this we'd have to check, but there shouldn't be. There's nothing on the bottom. So anyway, that's how you graph. With the calculator, using the numerical derivative. So this looks like y prime equals absolute value of x. No idea how that works. That's a product rule problem. I'd have to split it into two, one positive, one negative. Pretty cool. That's pretty cool. I enjoy slick math that I don't really understand. Okay, and when we graph this one I actually know why it does that. We get this. So y prime equals tangent of x. It's like, all right, final values, which function is differentiable? So basically look for problems, asymptotes, domains that are missing, things like that. We factor to the bottom, we get x minus 5, x plus 1. So we say that's where we're going to have problems. So I'm going to actually do this. Negative infinity to negative 1 union negative 1 to 5 union 5 to infinity. It also said, either way, I don't care what works for you. All right, third root, that should be fine. That should be no problem at all for everything. But I should graph it, make sure that there's no cusp here or something like that. Man, this makes me nervous. Let me see what's going on here. So third root, and I'll show you what I'm doing. I know I'm doing it off screen. 3x minus 6 plus 5. So I've just plugged it in. 3x minus 6 plus 5. Third root, 3x minus 6 plus 5. Graph. Looks like it has a vertical tangent there. I had a serious mistake on my my calculator. So we can't take the derivative there. Got it. All right, I finally figured it out. If I take the derivative of this, it's something to the 1/3. It ends up negative. I can't put in 0 under the square root. So 3x minus 6 is 0. Cannot equal 0. 3x cannot equal 6. X cannot equal 2. And if I graph it, as you just saw, there's a, well, that was horrible. That's not that bad. So I'll go back and be lazy and do this. So all reals, x cannot equal 2. All right, absolute value of x, it's fine. It's just going to be some weird graph. I made it look like there's a corner here, but there isn't. Yeah, no, it's fine. Oh, wait, no, there is a corner here. Man, I'd have to graph this. Very challenging stuff. Why would that be a problem? Derivative. Whatever, it's corner there, so no dice, can't take it. So we get all reals. X does not equal 0. And that's just from graphing. So I'm assuming something similar here. No, for some reason, no. Graph it. We get some big weird kind of thing. So all reals. Always graph it. I'm being a tiny bit lazy, but at the same time, I want you to graph it and see if you agree with me. I want to do all the work for you. Find all values for which a function is differentiable. Oh, I just love a good piecewise. So All right, so x plus 1 squared with the dot. And then 2x plus 1. Up to 3, 6, 1, 7, 1, 2, 7. And it's open and open. And then plug in 3. Now we're off somewhere else. So it's 1, 2, 3 here, solid, and that is, I believe, something like this. All right, now here's the weird part. You would say everywhere except that x equals 0 and 3. Well, let's check out the derivative from both sides. On the left, at 0, we get a 2x plus 1. Plug in 0, we get 2. On the right, derivative is 2. So, and we'll get more about this coming up later. This has the same slope, both left and right of x equals 0. So, well, here I would go with negative infinity to 3, union 3 to infinity, or all reals, x does not equal 3. Whichever you want. Now over here, we get a nice clean graph, no problems. Here we go with all reals. All right, show that the function is not the derivative function of the interval -1 to 1. So we graph it. We get solid, looks a lot like the GIF function. And we say, be as lazy as possible by derivative intermediate value theorem. F prime should exist every value from 0 to 1, and that's on the f of x, here to here. Since it does not, this function is not a derivative from -1 to 1. Horrible, horrible stuff. I'm trying to give you a taste of where the AP is going, but it's not even that bad. So, yeah. That function, if function is continuous, what's the relationship between A and B? Find the equivalence for A and B will make it both continuous and functional. Okay, lots to write down here. F1 must equal 3 minus 1 equals 2. So to be continuous at 1. All right. And this is not the one, it's over here. So what does it have to be over here? 3 minus 1 equals 2. If the top or x are less or equal to 1. All right. For continuity, A1 squared plus B 1 has to equal 2. All right. So therefore, A plus B has to equal 2. Now that's for continuity. All right, for differentiability, derivative of 3 minus x must equal derivative ax squared plus bx, which is 2ax plus b. So we have a second equation. 2ax plus b has to equal -1. Let's just go with elimination. 2ax plus b equals -1. Oh, I messed up. That's at 1, so this is 1. By the way, notice you can't cross that out. 2a plus b equals -1. And then I will put the other equation underneath it. A plus b equals 2. And we'll slap some negatives there for elimination. So a equals -3. Here's one of them. A plus b equals 2. -3 plus b equals 2. B equals 5. That's actually not too different a AP problem you might see. You don't have the tools to do the derivatives just yet. I've shown you before, but we're not quite there. The derivative of this is 0 plus -1. So I just wrote -1. The derivative of this is 2ax plus b. Then when x equals 1, it's 2a plus b. It's not an unusual problem. Definitely see something like it. That's it. Shocker. All right. Didn't realize we were done. Good luck and happy mathing.